Hi everyone, and once again welcome to my channel. In this today's session I am going to uh, talk about physics, and this is from the Ibdp course, and the topic name is electrical fields or electric fields, and there's one particular numerical you can see on the right hand side over here. It's a beautiful numerical, and this has been taken from a book called David Holmer, and it has been written by David Holmer. It's a course book, and it's the fifth edition. From that particular book, I have taken this particular question. Okay, so first let us have a look at this question. This question has A, B, C, three sub questions, and A part of the question says that calculate the electric potential at a distance of 1.5 kilometer from a point charge of minus 0.4.8 nanocoulombs. That is the A part of the question, right? So let us get started right away. A, the solution for A is asking you to calculate electric potential. Electric potential is denoted by VE. Okay, so he is asking you to find out the electric potential at a distance of 1.5 meter from a point charge of minus 0.48 nanocoulomb. So suppose you have a point charge, say Q1 over here. From here, if you take a distance of say 1.5 meter, right? So let us say that this is a distance of say 1.5 meter. Okay, so at this particular point, okay, say let us call this point as P. So at this particular point, he is asking you to find out the electric potential, right? This distance is 1.5 meter, right? This is 1.5 meter, and this Q1, the source charge, is of the magnitude minus 0.48 nanocoulomb. That's it. Okay, now this is a very easy question, okay, provided you know the formula. Okay, so the formula for VE, that is electric potential at the point P, can be given by this formula: K times the source charge Q1 divided by the distance of that point P from the source charge, and that we can take as R. Okay, so this will give you the potential, electric potential at this point P. Okay, so K, you will have to take the value as 9 into 10 raised to 9. Now this is a constant value, it is known as Coulomb's constant, and this is for the vacuum or the air. Okay, now here they haven't mentioned you anything about the medium, so if they have not mentioned anything about the medium, you can consider it as a vacuum or a air, and you can take K value as 9 into 10 raised to 9. This is the K value times Q1. Now Q1 is your source charge, so its value is minus 0.48 nanocoulombs. So we'll have to convert it into coulombs, so into 10 raised to minus 9 coulombs, right? And whole thing divided by R. R is nothing but the distance of that point P from the source charge, which is 1.5 meter, right? So remember here the distance should be in meters and the coulomb and the charges should be in coulombs. Okay, so if they are not in the meter or coulomb, you have to see that you are converting them into coulomb and meter respectively, and then carry on with the calculation. Okay, fine. So now my calculation goes this way: this 10 raised to 9 and 10 raised to minus 9, they become like they cut off each other. Okay, now we are left with 9 into minus 0.48 divided by 1.5, and there's a negative sign over here, so it will be minus of, now 9 into 0.48 divided by 1.5 works out to 2.88. Okay, so this works out to 2.88, right? And if I round it to 1 dp, okay, this will work out to around 2.9. Okay, so this is the value, 2.9 volts, right? Fine. So K is equal to 9 into 10 raised to 9. K is equal to 9 into 10 raised to 9 value you have to substitute. Q1 you have to take minus 0.48 into 10 raised to minus 9 because it was nanocoulomb. So you have to make it in coulomb. You have to convert it into coulomb. So it will be into 10 raised to minus 9. And the distance should be in meter, which was already in meter, 1.5 meter in the question itself. So your answer is minus 2.9 volt. Okay, there's a minus sign also. Here remember that if the source charge is positive, then the potential, okay, the electric potential due to that source charge will also be positive. And if the source charge is negative, then the potential created at any point in the field due to that negative source charge, that potential will also be negative. Now here the source charge itself was a negative charge, so the electric potential at the point P is also negative. Okay, so that was the A part of the question. Now let us move to the B part of the question, right? Now B part of the question says that this A is done. Another point charge is placed 1.5 meter from the first charge. Okay, calculate the potential energy of the system of the two charges when the second charge is number 1 minus 1.3 nanocoulomb, number 2 plus 0.90 nanocoulomb. Okay, now to deal with this B part of the question, okay, he is saying that another charge is placed 1.5 meter from the first charge. So first charge, that is your Q1, okay, which was minus 0.48 nanocoulomb. Okay, that is already there. Now this is Q1. Now he is taking another charge Q2, okay, and this is B1 first we are doing, okay, and that Q2 should be minus 1.3, a negative charge, okay, minus 1.3 nanocoulomb, okay, and this second charge is placed at a distance of 1.5 meters. So again this distance from here to here is 1.5 meter, right? Okay, so this R is equal to 1.5 meter. Okay, okay. Now what they have asked you to find out, calculate the potential energy of the system. Okay, here I would like to tell you something about potential energy, and these are very basic and very conceptual things that I am going to tell you now. Potential energy, okay, potential energy, of course, electrostatic potential energy we are talking about. So electrostatic potential energy due to a single charge, okay, due to a single charge is not defined. Okay, so there's nothing called the electric potential energy, okay, due to some charge, only a single charge. Okay, like there will not be any electric potential energy due to a single charge Q1 minus 0.48 nanocoulomb. Neither there will be a electric potential energy due to a single charge Q2 minus 1.3 nanocoulomb. Okay, so due to a single charge there will not be any potential energy. Potential energy, okay, as such is not defined only. There's nothing called potential energy. There's something called change in potential energy, that is delta PE. Okay, and this delta PE, this is known as change in potential energy. Okay, change in potential. This itself is referred to many a times as potential energy of a system. Okay, so when they are asking you potential energy of a system, that means there will not be a single charge, that there should be at least two charges, and in this case now we have these two charges, okay, Q1 and Q2. So Q1 and Q2 are making up a system of charges, and a system of charges, for a system of charges the potential energy exists, okay, and it is defined. So that potential energy, that change in, and it is always a change in potential. You can call it potential energy of a system, but actually it is change in potential energy of the system. Okay, so this is what you should, and this is defined. This is defined. Okay, so now this is something that you have to calculate over here. Now in my earlier classes I must have told you about this thing, the potential energy, or the rather change in potential energy, okay, is always equal to a negative work done due to any conservative force, that is minus WC. C stands for conservative force, right? In this case, now we are dealing with electrostatics, so this conservative force will be your electrostatic force. Instead of C, I am writing Fe, electrostatic force. Okay, so change in potential energy or just potential energy of the system is equal to a negative work done due to conservative force. To be particular, that conservative force now right now is nothing but electrostatic force, and that is denoted by Fe, so minus W Fe. Okay, this is also many a times known as internal force. Okay, so WIN or INT, right? So there are so many ways you can say. In some books, they say potential energy is equal to negative WC. In some books they say it is equal to minus WFE. In some book they say it is equal to minus W internal. Okay, so whatever it is, but all mean one and the same thing. Conservative force, this is a kind of conservative. There are three types of conservative forces. Okay, there's something called electrostatic force which are conservative. There's something called gravitational force which is conservative, and there's something called spring force. Okay, that is also conservative. Okay, and all conservative forces are also known as internal forces. Okay, so work done by internal is same as work done by Fe, same as work done by conservative force. I hope you understand this concept. So now they have asked you to calculate potential energy of the system, so we are going to find the potential energy of this system. Is that clear? Now how we are going to find the potential energy of this system? Okay, now let us see how to deal with this question. Okay, so in this case we are going to use this formula, potential energy is equal to negative work done. Okay, so let us try to find out the work done due to internal force, which is same as the work done due to conservative force or the work done due to the electrostatic force. So WINT will be equal to, now work done is always equal to, let us put a minus sign also over here. Okay, because potential energy is that, right? So let us find out this only. So minus of WINT will be equal to force. Now if it's a work done due to internal force, this will be force which is electrostatic force. Okay, Fe, right? Now let me write here, just not to make you more confused, I'll write here work done due to electrostatic force. Okay, in this case we are dealing with electrostatic force, right? So work done due to negative work done due to electrostatic force is equal to electrostatic force times the distance. Okay, that is dx. This is the general formula. Now in this formula, what will be your Fe, electrostatic force? Electrostatic force is given by this formula. It is K times Q1 Q2, that is the product of the two charges, divided by the square of the distance between them. Got it? So this is the formula for Fe, right? And that multiplied by dx, that is the distance between the two charges, so times r, right? So Fe is only this much, so I don't want to put this into r. Okay, this is Fe. So my work done, negative work done due to Fe will be equal to, okay, let me not, okay, it will be equal to Fe. Now Fe is this, okay, K times Q1 Q2 upon R square multiplied by this dx is the distance between the two, and that is also R. So take R. Okay. So this R and R is going to cut, and you will be left with only R. So basically this is what you will get. So let us plug in the values. So K will be 9 into 10 raised to 9, right? Q1 and Q2 will be, Q1 is minus 0.48. Now because it is nano, I'll take 10 raised to minus 9 times another charge is also negative, so it will be minus 1.3 into 10 raised to minus 9 again in coulombs, and the whole thing divided by R, and the R is nothing but 1.5 meter, right? Now let us try to solve this. Okay, so this will give me the answer as, now see there's a negative sign also over here. Okay, so that negative sign will be coming. Let me do one thing. This potential energy is negative of this. Let us take only this formula for WE. Okay, WE is this, WFE is this. Okay, then we are going to put that negative sign, right? Because potential energy will be minus of that. So now this 10, I'm so sorry. This was 10 raised to 9. Rest is all okay. Okay. So what happens is this 10 raised to 9 and this 10 raised to minus 9 is cut off. It's gone. Now we are left with only 9 times this minus into minus will make it plus. Okay, so I'll get a plus sign over here. So 9 into 0.48 or 48 multiplied by 1.3. Okay, and you have one more 10 raised to minus 9 over here divided by a 1.5. Right? But now it will be plus. Okay, so if you work out this, let me see what answer I am getting. So 9 into 0.48 into 1.3 equal to divided by 1.5 is 3.7. Okay, 3.7. It's 3.74, but I'll write 3.7, and this into 10 raised to minus 9. Okay, now this is, and there is a plus sign. Okay, so this is positive 3.7 into 10 raised to minus 9, and this is work done, so it will be joules, right? But remember here, I told you in the beginning that potential energy, okay, is equal to, you can see this, potential energy is equal to the negative of the work done due to conservative force. Now this work done due to conservative force, that is electrostatic force, we got as positive, but it should be negative. So therefore negative work done due to this Fe, okay, that is electrostatic force, will be minus 3.7 into 10 raised to minus 9 joules. Therefore you can say that the potential energy of the system is negative 3.7 into 10 raised to minus 9 joule. Okay, so potential energy can be negative, it can be positive. Okay, now all that is theoretical aspect, but the answer for this particular numerical is potential energy of the system is a negative 3.7 into 10 raised to minus 9 joules. Now if you see the second part of this question, he has told you to replace this Q2 by 0.90, a positive 0.90 nanocoulomb. So for B2, okay, only I'll make the changes in the calculation. Okay, Q2 I am going to make it as 0.90 nanocoulomb, a positive one. Okay, so here again your work done due to internal force, okay, or rather Fe, work done due to electrostatic force. Okay, and let me draw the diagram. This is Q1, which is remaining minus 0.48 nanocoulomb, and you have this Q2. Now this time Q2 is a positive 0.90 nanocoulomb. Rest of the things is remaining same, that is this distance between them is 1.5 meter. Okay, so work done due to electrostatic force, okay, we'll calculate this as Fe dot dx. Okay, fine. Now what will be Fe? Fe will be equal to, electrostatic force will be equal to K times Q1 Q2 upon R square, isn't it? Now your work done due to Fe will be equal to K into Q1 Q2 upon R square. Okay, that is for Fe. I have substituted this times dx. Dx is the distance between the two charges, and that is R. Okay, so now this R and this will go. So my answer for work done due to electrostatic force will be equal to K times Q1 Q2 divided by R. Now let us substitute the values and try to find out this. Okay, so K I will take very nicely, 9 into 10 raised to minus 9. My Q1 is unchanged, it is 0.48, it's a negative 0.48 times 10 raised to minus 9. Remember, you have to convert into coulombs. Q2 is this time positive 0.90, again it is nano, so it will be 10 raised to minus 9 coulomb, and whole thing divided by R, that is the distance, which is 1.5 meters. Okay, this 10 raised to minus 9 and this is 10 raised to, plus 9. Okay, so this 9 into 10 raised to 9 and this 10 raised to minus 9. Okay, they will cut each other. Okay, now you are left with 9 times, now see there is a negative sign over here, there is a positive sign over here, negative into positive will be negative, so this time you are getting minus. Answer you are getting for W, work done due to electrostatic force, in negative. Okay, so 9 times 0.48 times 0.90 times 10 raised to minus 9, that is this 10 raised to minus 9, whole thing divided by 1.5. Okay, now I am going to do this on my calculator. So this sign will be remaining minus, and my answer should be 9 times 0.48 times 0.90 divided by 1.5, and that gives me the answer as 2.6. If I round it to 1 dp, I am getting 2.6. So minus sign and then 2.6, and don't forget this 10 raised to minus 9 was always there, and this will be joules. Okay, so work done due to electrostatic force, that is work done due to internal force, is negative this time. Previous question we got positive work, this time we got negative. But you have to find out the change in potential energy of the system. So I told you potential energy of the system is equal to the negative of the work done due to the electrostatic force. So that will make this as, now the work done was minus 2.6, so negative of minus 2.6 will be positive. So it will be plus 2.6 into 10 raised to minus 9 joules. So this is the answer. Got it? So B part of the questions, we got the answer as for the first part, okay, B1, we got the answer as minus 3.7 into 10 raised to minus 9 joule, and for B2 we got the answer as plus 2.6 into 10 raised to minus 9 joule. Okay, okay, now having done that, you have one more part of this question, that is C. So B is done. C, for each of the charges in part B, that is these two, 1 and 2, calculate the work needed to change the separation of the system to 0.50 meter. This is interesting. C. So for the C part of the question, okay, the source charge Q1 is remaining same, minus 0.48 nanocoulomb. This is as it is. Now what is happening, one by one, now C also you have 1 and 2. Okay, so in the first case you are going to take a charge, okay, same as B, no, in B, yeah, for each charge in the part B. So for B1 it was minus 1.3 nanocoulomb. Okay, so that you are going to take and you are going to bring it to a distance of 0.50. Okay, so we'll take this Q2 as minus 1.3 nanocoulomb. Okay, and this charge from somewhere, okay, you are going to bring it, okay, to a point, say over here, okay, which is at a distance of 0.50 meter. Okay, so this distance you can take as r, and assume that this distance, okay, that is let me draw a line to indicate that. Okay, so this distance, okay, let us assume to be x, right? This is x. Okay, so and this is r, right? Now let us read the question once again. The C part of the question says that for each of the charges in part B, that is minus 1.3, and second time it will be 0.90 nanocoulomb positive. Calculate the work needed to change the separation of the system to 0.50. So initially what was the separation? Initially the separation was 1.5 meter, isn't it? In the B part, can you see in both the question, the separation was 1.5 meter. From this 1.5 meter, the separation has to be brought down to 0.50. So this separation x is 1.5 meter. Okay, from 1.5 meter, that is the distance between Q1 and Q2 when it is 1.5 meter. From that distance, you have to bring to this point. So suppose this is say point M, and this is point N. So you want to basically bring this charge Q2 from M to N. And in that process of bringing this charge Q2 from M to the position of N, what is the work done? That they have asked you to find out. What is the work done? Got it? So here you are going to use the formula work done due to internal force, or you can say work done due to Fe, okay, will be equal to, now here you know what is happening. See, the distance keeps on changing. Here it is distance is 1.5 meter. When you come to this point N, the distance has changed to 0.50 meter. And you know that the force, electrostatic force, is inversely proportional to the square of the distance. Okay, so this electrostatic force is dependent on the distance, right? It is dependent on the distance. It is inversely related to the distance, right? So you can say that Fe is a variable force. It is not a constant force. It is a variable force. Okay. So for a variable force, the formula for work done due to that variable force Fe is integration from initial to the final. So initial is x and the final is say r. Initially it was at a distance of x, and final position is when the distance is r between them. So it will be initial to final, x to r, integration, lower limit is x, upper limit is r, Fe dot dx. This is the formula for work done. Okay, and using this formula we are going to get the answer. So here Wfe, the work done because of this electrostatic force, will be equal to integration. Now x is 1.5, r is 0.50, so I am putting the values. Okay, Fe will be Q1 Q2 K divided by the x square. Okay, divided by the x square, because that is the original situation between Q1 and Q2. Initially the distance is x square multiplied by dx, okay, or with respect to dx. Is that clear? Okay, now if you know a little bit of calculus, okay, you can do this. Now in this case, the constant thing I am going to remove it out. So K Q1 Q2 is constant, that I am taking out, and integration 1.5 and here 0.50, okay, and here I am left with 1 upon x square, right, dot dx. Okay, this will again work out to k q1 q2. Now integration of 1 upon x square, integration, this is definite integration. Okay, you have limits, right, lower and upper limit. So integration of 1 upon x square is minus 1 upon x, right? Now this much calculus I assume that you people must be knowing, and that is why I am not going to explain you that part of it, because that is purely mathematics and I am here to deal with the physics topic. Okay, anyways, 1 upon x square, the integration is minus 1 upon x, and the limit will be 1.5 and 0.50, right? Now we can work out this. So your work done will be equal to, now let us put the values. So k will be 9 into 10 raised to 9, q1 will be a negative 0.48 times 10 raised to minus 9, q2 will be a negative 1.3 times 10 raised to minus 9, right? And this part, you know, this will be minus 1 upon, now first I'll put 0.50, minus of minus will be plus, and 1 upon this value I'll put for x, 1 upon 1.5. Okay, this can be, this will be going. Okay, now 9 into minus, so first I'll deal with the sign, so it will become plus, so this is plus. 9 into 0.48 into 1.3, let me work out that. So that should be 9 into 0.48 into 1.3 is equal to 5.616. Okay, I worked out only this, and this, and this is there into 10 raised to minus 9. This is always there. Now this thing I can work out in another way. Now minus 1 upon 1.50 plus 1 upon 1.5 can be written as 1 upon 1.5 minus 1 upon 0.50. Okay, this in turn will be plus 5.616 times 10 raised to minus 9, and 1 upon 1.5, let me see, 1 divided by 1.5 is equal to 2 upon 3, this is 2 upon 3, minus 1 upon 0.5, that is 1 upon half, this will work out to 2. Okay, now this should work out to plus 5.616 into 10 raised to minus 9, and this bracket quantity will be 3 2s are 6, 2 minus 6 is minus 4 upon 3. Now again I am getting plus and a minus, so my ultimate work done due to the electrostatic force will be a negative one, because plus into minus is minus, and 5.616 times 10 raised to minus 9, and this 4 upon 3, okay, minus sign I have taken here. Okay, it has been multiplied by this plus sign, and you get a minus sign over here. So just 4 upon 3 is 1.33, right? It's a recurring decimal. So my final answer will be a negative 1, and let me see, 5.616, right, times 1.33 is equal to a 7.46. So let me, this I did, okay, this much, so negative 7.46 I am getting, so let me take 7.5, okay, minus 7.5, and this 10 raised to minus 9 is always there, and because this is work done, it will be choose. So this is the answer for the C part of the question and C part of question number 1. Okay, C1, this is the answer. Same way C2. For C2, what you have to do is same thing. Okay, only thing is your charge Q2 is going to change, isn't it? Charge Q2 is going to change. Okay, so shall I start the working from here itself? Okay, where should I start from? Okay, let me do the entire working, right? So again here, C2 you have to find out the work done due to electrostatic force, and this is equal to integration. Now the distance will be same, okay, so x to r, this will be Fe dot dx, okay, same thing, right? So this will be equal to 1.5, this will be 0.50, okay. Now your Fe will be k times q1 q2, okay, upon x squared into dx, right? So everything is going to remain same, only this q2 this time is going to be different, okay. This q2 is equal to plus 0.90 nanocoulomb, okay, that's the only difference. Okay, when you work out this, so let me do this. So k q1 q2 being constant, I'll take it out, and 1.5 0.50, here I'll be left with 1 upon x square dx. This will be k times q1 q2, and this integration of 1 upon x square works out to minus 1 upon x with the lower limit 1.5, upper limit 0.50. That's it. This will work out to, now this all I am getting for, I am working out for the work done, okay, work done due to electrostatic force. So this will be equal to 9 into 10 raised to 9. This is k value. Q1 value is negative 0.48 into 10 raised to minus 9, okay. Q2 value is positive 0.90 into 10 raised to minus 9, okay. That's it. Then the bracket quantity will be same as this, okay. So it will be like should I take minus 4 by 3 directly? Okay, let me work out that also. So this will be minus of 1 upon x, first we will take as 0.50, minus of minus is plus 1 upon 1.5, right? So this should be equal to, this is gone, okay. Now 9 into, now first let me take care of the sign, plus and minus, so this will be minus, and then 9 times 0.48 times 0.90, let me check what it is. 9 times 0.48 times 0.90, and that gives me 3.88, so 3.88, okay. This 10 raised to minus 9 is remaining, and this bracket quantity is going to be 1 upon 1.5 minus 1 upon 0.50, okay. So this will be minus of 3.88 times 10 raised to minus 9, and this 1 upon 1.5 should be equal to, what was it, 1 upon 1.5, 2 by 3. So 1 upon 1.5 is 2 by 3, and this is 2, okay. So this will be a minus 3.88 times 10 raised to minus 9, and this should be 3 2s are 6, 2 minus 6 is minus 4 upon 3. So now this minus and minus will become plus, and this is 3.88 times 10 raised to minus 9, and 4 upon 3 is 1.33, okay. So my final answer will be a positive. So this time I am getting the work done as positive, and this quantity, that is 3.88 times 1.33, I am getting as 5.16, okay. So I will round it to 5.2, yeah, and this 10 raised to minus 9 was there, okay. This 3.88 times 1.33, I got 5.2 into 10 raised to minus 9 joule. This is the answer for the C2 question, okay. So I have worked out this entire question, okay. It was a beautiful question, as I told you, from this David Holmers course book, 5th edition. And in this question, you know, there were so many things that you have to use conceptually, and without making any mistake, you know, you can do in this way. This is a proper way of understanding and doing this particular numerical, okay. So that's all for today, and in the next video I'll come up with more numericals on the same topic, okay. So till then, goodbye, take care all of you, see you.